Hello everyone, my name is Sasha and welcome to the second video in the curve sketching series. In the first video, we talked about the basic concept of curve sketching. We ran through this list of curve sketching and we talked about sign diagrams. All of this will be used in this video, so if you don't understand what I'm talking about, it might be helpful to go back and look at the previous video, but if not, we can go ahead and jump right into it. So here is a more complicated function that we wouldn't really be able to solve as easily with our basic understanding of finding the x or finding the y-intercept and therefore finding the slope and then being able to draw the function, because this is a function with a third degree polynomial and that makes things a lot more complicated. However, thanks to these steps, we will be able to draw the function just as accurately as we would have been able to if the function was a linear function. However, it's going to be a little bit more complicated. Things are going to start off pretty similar. We're going to first start off with our first step, which is using the y-intercept, which is basically taking f of 0 of this function. As you can clearly see, the first two terms would cancel out completely, leaving just behind this third constant term, which means that f of 0 is 3. We can go ahead and mark that on our graph right here, just to keep note of it, but that's easy enough. The second thing that we would do is to look at the x-intercepts. However, because this is a third degree polynomial, there isn't any reliable way to be able to find the, because this is a third degree polynomial and there's other x's involved with other degrees, there's no really reliable way to find x-intercepts, so we're going to go ahead and leave this part for now. Thirdly, we're going to take a look at the asymptotes and how the graph is behaving in the infinities. If there was a denominator to this function that had x involved, x in the denominator, that would create an asymptote. However, because that's not true, we can say that there probably aren't any asymptotes in this graph. Just to be sure, let's go ahead and look at the end behavior of this graph. So let's take the limit as the graph approaches infinity. So as the graph approaches infinity in this function, the most important thing that we want to look at is this first term. And that's because this first term is going to be the main thing that's going to be involved as the numbers being put into the input get arbitrarily large and positive. If x was 2, for example, x to the third power would only be 8, and x to the second power would be 4. And these numbers are fairly close to each other, so this negative 4x term would have a lot more weight on the sign of the function overall. However, as we get into larger numbers, like we don't even have to go that big, we could just go to 50. 50 to the second power is 2500. Consequently, 50 to the third power is 125,000. As you can see, these are very different numbers, so this term is going to be king when it comes to evaluating the function in the limit as it approaches arbitrarily large numbers. So when the number is arbitrarily large and positive, aka infinity, this term is going to be positive. So we can say that as the limit of x approaches infinity, this entire function is going to also approach infinity. And we can kind of mark that on our graph. And then as it approaches negative infinity, however, we can see that this first term is going to yield negative numbers, because a negative number to the third power is still going to be a negative number, so this entire first term will be negative, and therefore the entire thing overall will be negative. So we can go ahead and annotate that on our graph. So basically what we found out from the asymptotes and the end behavior section of this is that as x approaches infinity, the y values, or the outputs, also approach infinity, and as x approaches negative infinity, the y values also approach negative infinity, and there are no asymptotes to be concerned about. Next, we will go ahead and take a look at the first derivative. Following this power rule, we can very easily take the derivative of this function, which I will be notating as f dashed of x from now on, and we can go ahead and mark this down. So we'll get 18x squared minus 8x. And the constant will not be involved in the derivative, as constants don't have any bearing on the slope of functions. Then we can go ahead and simplify this by extracting an x or factoring an x out of this equation. And that might seem a little bit confusing, but as you can see, both of these terms here both have an x in them, so we can go ahead and factor that out to the outside and basically like reverse distribution it. So we kind of think, what does x need to be multiplied by to get this first term of 18x squared? And the answer is 18x. And then we go to the second term. What does x have to be multiplied to get negative 8x? And the answer is negative 8. And we can go ahead and check our work. 18x times x is 18x squared, and negative 8 times x is negative 8x. So that go ahead and like checks out. And basically what I'm saying is these two functions are equivalent. However, the second one is going to be more helpful in the second part, which is calculating f of 0. Like I said before, when the derivative is 0, we are going to be able to find the maxes or mins in the graph, the point where the slope changes from being positive to negative, or negative to positive. So we want to be able to use this equation to locate the zeros of the function, and given that this is a quadratic expression, we could use the quadratic formula. However, by factoring this out nicely, we could do it without using the quadratic formula. Basically, what we'll do is set each of these brackets equal to 0, x equals 0, and 18x minus 8 equals 0. And this first one is very obvious. Obviously, x is going to be 0. There's no calculations needed. However, the second one is a little bit more tricky. It's just a simple two-step equation with 18x equaling 8. We'll divide by 18, or if you want to be fancy, you can multiply by 1/18 on both sides, leaving you with a result of 8 over 18, or in a simplified form, 4 over 9. So this gives us an idea of where the zeros of this function are. And we know that these are either maxes or mins, however, we're not really quite sure which. This is where sign diagrams come in, and we can take a look at this function, f dashed of x, using a sign diagram and get a better idea of how the function f dashed of x is behaving, which in turn gives us a good idea of how the function f of x is behaving. So we have negative infinity on this side, positive infinity on this side, and our two important points of 0 and 4 over 9 in the middle. And obviously these both correspond to zeros in the function f dashed of x, but the question is, how is the function behaving in between all of these points? And so how we can do this is we can think about what would happen if we used a number in this bracket. So if we use -1, for example. We can go ahead back to our function. This, if we replace -1 with all of our x's, this is going to be negative, and this is going to be negative minus a negative, which is a negative, and a negative times a negative equals a positive. So basically, this is negative, and this part is negative, and they are both going to multiply to be positive. So therefore, we can say that this portion is going to be positive. In the middle, we want to do the same thing. We can use a number that's in between. I'm partial to 1/4 for this problem, but it doesn't particularly matter. And then here we have this side is going to be positive because it's 1/4, which is a positive number. And then this is going to be positive, but it won't be big enough to cancel out this negative number that we're subtracting by. So this inside of the bracket is going to be a negative number, which means that overall this is going to multiply out to be negative. We can go ahead and annotate that here. And then on this side, we can do the same thing with another number. We may as well use 1. This is going to be positive. This is going to be positive because it'll be a number big enough to cancel out this negative number, and they will both multiply together to be positive. So we can go ahead and annotate that on our graph, and here we have a good idea of how the function is behaving. Now we can annotate what that means for our function f of x. It means that the slope is going to be positive over this interval, negative over this interval, and positive over that interval. And from that, we can see that this is going to create a maximum, and this is going to create a minimum. And then the last thing that we have to do is we know that these values correspond to zeros in the function f dash of x, but we're not sure how they correspond to what y values in the overall function f of x. So basically what we have to do is plug in the y value, or plug in the x values 0 and 4/9 to figure out what y values they correspond to, so we can go ahead and plot them on our chart. Obviously we know that f of 0 is 3 because we already calculated that for our y-intercept, which means that this point right here is both a y-intercept and a maximum. And 4/9 corresponds in this function. I already did the math, so I can just go ahead and tell you. It's roughly 2.736. So we can go ahead and kind of plot that on our graph. Let's see, it'll be a little bit less than a half and pretty close to being up here. We'll say we'll go about there, and we can label that point and write that it is going to be a minimum. And that concludes all the work that we are going to be doing in this video. In the next video, we will cover the second derivative, which tells us about concavity and inflection points. Then we will be checking the graph in Desmos to see how we did, and then I will go over a couple different tips and tricks that you can use to tackle more difficult problems, like ones that have things in the denominator and things like that. So thank you for watching. I hope to see you in the next one.